Consider a current-carrying conductor in the form of a circular loop of radius A with center O at the origin of the coordinate axes. The plane of the loop is along the YZ plane. Let I be the constant current passing through the circular loop. To simplify the understanding of the topic, we neglect the ends of the loop from where the current enters and leaves the loop. We know that any current-carrying conductor produces a magnetic field whose direction is given by Ampere's right-hand thumb rule. Thus, the magnetic field lines for the current-carrying loop are as shown. To have a better picture of the concepts that we are dealing with, we do not show the magnetic field lines in the current module. X-axis is the axis of the loop which is always perpendicular to the plane of the loop. Consider a point P be on the axis of the circular loop at a distance x from the center of the circular loop. Let dl be the small element of the circular loop located at position 1 as shown, and dB be the magnetic field induction at the point P due to the current I passing through the small element of the loop. Let R cap be the vector joining the point P on the axis of the circular loop and the small element dl, and R be the distance between the small element dl and the point P. According to Pythagorean theorem, R is equal to square root of x square plus a square. Let this be equation 1. Squaring on both sides, the equation can then be represented as R square is equal to x square plus a square. Let this be equation 2. According to the Biot-Savart law, the magnetic induction at the point P due to the current passing through the small element dl, dB is equal to mu naught by 4 pi into I into modulus of dl cross r by r cube. Let this be equation 3. As the circular loop is symmetric about its axis, even if we consider the small element of the conductor at any other point on the loop, the length of the element dl will always be perpendicular to the displacement vector r at that location. However, the magnitude of dl cross r is equal to dlr sin theta, where theta is the angle between dl and r. Here, the angle between dl and r is 90 degrees, and sin 90 degrees is equal to 1. Therefore, the magnitude of dl cross r is equal to dlr. Let this be equation 4. We now replace the modulus of dl cross r with dlr in the equation 3. On simplifying the expression, we get the magnetic induction due to the small element of the loop as dB is equal to mu naught by 4 pi into IDL by r square. Let this be equation 5. We had already established that r square is equal to x square plus a square. On substituting this value in the expression for magnetic induction, we get the magnetic field at point P due to the small element dl of the current carrying circular loop as dB is equal to mu naught by 4 pi into IDL by x square plus a square. Let this be equation 6. The magnetic field induction dB at the point P is perpendicular to the plane containing dl and r, and its direction as given by right-hand thumb rule. We now resolve this magnetic induction at P into two components. One along the x-axis represented as dBx, and the other perpendicular to the x-axis in the YZ plane called as the normal component of the magnetic induction represented as dBy. If theta is the angle made by dB with the x-axis, then the horizontal component dBx is equal to dB cos theta. Let this be equation 7. The vertical component dBy is equal to dB sin theta. Let this be equation 8. Let us now consider another small element of length dl on the circular loop at a position diametrically opposite to the first element as shown. This element at position 2 is at the same distance from the point P on the axis of the loop as that of the element at position 1 on the loop. Thus, the magnitude of the magnetic induction at point P due to the element at position 2 is the same as that due to the element at position 1. Let this be dB dash. Thus, dB is equal to dB dash. Let this be equation 9. The direction of dB dash is such that it makes an angle theta with the x-axis. This is due to the symmetry of the circular loop. The magnetic induction dB dash can also be resolved into its horizontal and vertical components, dB dash x and dB dash y as shown. Here, dB dash x is equal to dB dash cos theta. Let this be equation 10. And dB dash y is equal to dB dash sin theta. Let this be equation 11. The horizontal components of the magnetic induction at P due to both these elements dBx and dBx dash are equal in magnitude and are in the same direction. The normal components of the magnetic induction at P due to the small elements at positions 1 and 2 are equal in magnitude and are in opposite directions. Hence, their resultant is 0. This would be the case for all the elements on the circular loop, and hence the net normal component of magnetic induction for a circular conductor at the point P will always be 0. The net magnetic induction at the point P is now the sum of all the components of dB along the x-axis. By the geometry of the figure, the angle between the radius of the circular loop and the line joining the element to the point P is theta. Cos theta is equal to A by R, which is equal to A by square root of x square plus A square. Let this be equation 12. On substituting equations 12 and 6 in equation 7 and simplifying, we get dBx is equal to mu naught by 4 pi into IADL by x square plus a square whole power 3 by 2. Let this be equation 13. The net magnetic induction B due to the total circular loop at P can be obtained by integrating the horizontal components of magnetic field induction due to the small elements of the circular loop. That is, B is equal to integral of dBx. Mu naught by 4 pi, the radius of the loop A, current in the loop I, and the distance of the point P from the center of the loop X are the constants. Hence, the equation can be written as B is equal to mu naught by 4 pi into IA by x square plus a square power 3 by 2 into integral dl. Integral dl is equal to L, the perimeter of the current loop, equal to 2 pi a. Therefore, on simplification, we get the net magnetic induction on the axis of a current-carrying circular loop at a distance x from the center of the loop as B is equal to mu naught I a square by 2 into x square plus a square power 3 by 2. Let this be equation 14. And the direction of the field at P is along the x-axis. If we consider the point at the center of the circular loop, then the value of x becomes 0. Substituting x equal to 0 in equation 14 and simplifying further, we get the magnitude of the magnetic induction at the center of the loop as B is equal to mu naught I by 2a. Let this be equation 15. Thus, the magnetic induction due to the circular current loop is the maximum at its center. If we consider a current-carrying circular coil that has n number of turns, then the magnetic field induction due to these n loops at the center is equal to n times the magnetic field induction due to single loop, since all the magnetic inductions due to individual loops act in the same direction. That is, B is equal to mu naught Ni by 2a. Let this be equation 16. From the expression, it is clear that the magnetic induction B at the center of a circular coil is directly proportional to the number of turns n when the current I and the radius of the coil A are constant. Similarly, B is directly proportional to I when n and A are constant. B is inversely proportional to A when n and I are constant.